if we look at the Lewis structure of nitrate, NO3 with a -1 charge, nitrogen has 5 valence electrons, oxygen has 6, 3 times 6, and a negative means that we have an extra electron. So really, it's 6 times 4 here, so we have 24 electrons to play with. Divide by 2, we have 12 pairs we can put around our Lewis structure. So first off, I put nitrogen in the center because it's the least electronegative. Oxygen's around it, space them out a bit. 1, 2, 3, I use up 3. I have 9 valence electrons left. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, all these oxygens have their octet, however, nitrogen does not. So let's pull a pair of electrons off of this oxygen and bring it down, making that double bond. But why did I have to pull the electrons off this top one? Couldn't I have also pulled it off of here? I could have. I could have said nitrogen, single bond to an oxygen with the full octet, double bond to an oxygen over here, and single bond to an oxygen with a full octet over there. Or, why did it have to be this one? I could have pulled from the other one. So now I could also have this, where I have nitrogen, oxygen, oxygen, double bound to another oxygen. Fill in my octets. And the truth is, all 3 of these structures are valid. These are called resonance structures. We show that they're resonance structures by doing a double arrow between them and enclosing them in brackets. Since they all have a -1 charge, we have to include that outside the brackets. This picture fails to show those brackets. In order to receive full points on the AP exam, you will have to put brackets around resonance structures for each thing and separate them by a double arrow, like this is showing in this picture. And if it has a charge, please put the charge outside the brackets. Now, so based off of the Lewis diagram, we would expect that in the case of this first resonance structure, that the oxygen here is closer to the nucleus of the nitrogen, in this case of a double bond, because they're double bound. Double bound means there's a greater electron density between this nitrogen and this oxygen, therefore their nuclei will be more attracted to that electron density and pull closer together than in the case of a single bond. And the same is true of a triple bond. A triple bond, the nuclei are extremely close together because there is an extreme electron density between them. However, experimentally, nitrate doesn't behave as though it has a double bond and 2 single bonds. It behaves as though it has something between it, or something between those two, between a double and a single, for all 3 of its bonds. And how long, or the length of the bond, determines how strong that bond is. A triple bond is the strongest bond of all because there is a very, very strong, very, very high electron density between the 2 nuclei, which will keep them close together, compared to a double bond, which has less electron density, and a single bond, the least, where the 2 nuclei are attracted to that central electron density. However, there are other players in play. In my baby chem class, if you had me for baby chem, I show this by I hold a person's hand. I hold just one of their hands. There's a great distance that is between my body and theirs. If I hold both their hands, we now have to face each other. There's less distance. The other person can't squirm away from me because this is a creepy situation for them. And if we have a triple bond, that'd be like me crossing one of my legs with one of theirs and holding both of their hands. Now our bodies are really close together, and it is awkward for everyone because we are really close together. And it'd be like if we were playing Red Rover, which would you rather try to go through? Me holding just one person's, or holding just one of my hands with another person, holding both hands with someone, or both hands and a leg. both hands and a leg, you're going to have a hard time breaking through that in Red Rover. It's the same is true with bond length. The greater the bond length, the weaker the bond. Now remember, every single bond contains a sigma bond, and if you pack on more bonds, like you become a double bond, you gain a pi bond. You gain another bond, form a triple bond. That's 2 pi bonds and 1 sigma bond. In order to form a sigma bond, you have to have end-to-end overlap, where the end of a valence electron's orbital cloud, if you will, overlaps with the orbital cloud of another. And the same can be true of a p orbital. So s and p's can come together to form sigma bonds. In order to form a pi bond, though, you have side-to-side overlap, where the sides overlap one another. So this would be a pi bond along, let's say, the y-axis. You could also have one along the z-axis, which would bond out here and back here. All of which would contribute to a greater electron density between the two nuclei and bring them closer together. So bond length can contribute to the strength of a bond, and how that bond behaves is its bond order. And it's simply the number of bonding electrons shared by 2 atoms in a molecule. Well, 2 or more atoms in a molecule. So it's simply the number of bound pairs or bonded electrons in pairs divided by the number of atoms bound to the central atom. So in the case of nitrates, we have 1, 2, 3, 4 bound pairs, and there are 1, 2, 3 atoms bound to the central atom. So the bond order for nitrate would be 1 1/3. If the bond order is 1, that means you simply have a sigma bond, because you would have a bound pair over 1 atom, or 2 bound pairs over 2 atoms. Those would be all single bonds. If the bond order is 2, that means you have 2 bound pairs, so 1 sigma and 1 pi. Or if it's 3, that'd be 3 bound pairs divided by 1 divided by 1 linked to the central atom, or some derivative of that. Fractional bond orders exist when there is a resonance structure, which means that the bond energy, or the amount of energy necessary to break apart an molecule of nitrate, is somewhere between a single bond and a double bond. It's actually somewhere 1/3 more, because this falls between 1 and 2 in bond order. So there's a relational difference, or relationship between the bond order and the energy necessary to separate them. Another resonance structure, one that's very common, you will probably often asked to reproduce, is benzene. Benzene is an organic molecule consisting of 6 carbons and 6 hydrogens. It forms what's called an aromatic ring. And it's particularly stable because of these double bonds between the carbons. However, those double bonds could also be between this carbon here, and this carbon there. So this benzene is a resonance structure. And when it forms its ring, its 6 p orbitals overlap side to side, and you get these delocalized orbital clouds. However, what I really want you to be able to do is simply know that benzene, these are the 2 resonance structures for benzene. You can sometimes see benzene written as this. Either one of those. This 6-sided shape with the circle in the center is a universal understanding that that's benzene, because it shows that delocalized ring of electrons above and below it. Or the dotted lines. Another way of showing resonance structures is to show where possible double bonds could exist in multiple forms is with dotted lines. Regardless of how you draw benzene, let's move on. Bond dissociation energy, or D, is the energy required to break a chemical bond. It's also known as bond energy. And the key to this is to remember that anytime you break a bond, it is an endothermic process. It requires energy to break a bond. Any of the values given to you will be taken in the gaseous stage, much like first ionization energy and electron affinity had to be in the gaseous stage. Bond dissociation is in the gaseous phase, and it has an error of plus or minus 10%. Bond dissociation energy can be calculated using delta H equals the bonds broken minus the bonds made. And this is the only time in AP chemistry so far that you will take reactants and subtract from it the products. So it's the bond energies of the reactants minus the bond energies of the products. This is backwards from the Big Mama equation that we did in thermodynamics, where it was reactants or products minus reactants. In fact, this is backwards from every other reaction. However, when they're talking about bond dissociation energy, you're going to flip it. It is reactants minus products. In which case, the energy released will be greater in exothermic reactions, meaning giving you a negative delta H. If you have an endothermic reaction, then you'll have a positive delta H.